start from 2 and then we'll go back and look at 1 and 3. So on the graph, where are the reactants? Okay, at the beginning. Good. So 50 kilojoules. The reactants are here.
Transition state.
Okay, so the very highest one is your. Okay, it makes sense. Like when you transition, you're going from one thing to another, so your transition state is there at the top. Okay, so how much energy do the reactants have? 50, and the products have how much energy? 100. So, which one has more energy? Product. How much more energy do the products have? 50. So we had to gain 50 to get from the reactants to the products, right? So that means this is, we had to gain 50. So we had to take in energy to go from 50 to 100. So this reaction has to be endothermic. For us to get from 50 to 100, we had to take in energy.
So if it was exothermic, the graph would be?
Yes. So if it was exothermic, the products would have to come down below the reactant.
Oh.
Okay.
Okay, so that's what you think boiler is exothermic.
How can I give you your blood?
This is AP, so you can take it next year if you do really well in this year.
Why everybody keep saying it's AP like I can't get AP?
Because you have to take the first chemistry before you can take AP chemistry. They've already had 1 whole year of chemistry.
Oh.
It's not we're not dissing. All right. So that's the way you calculate delta H, is looking at reactants and products. Okay. So how much energy, what was the difference between reactants and products? 50. So delta H is 50 kilojoules. I've seen this question a lot on the test. Well, they have all these lines. So they'll do like a line here, reactants to products. That would be your delta H line. Okay, the difference there. We'll look at the formula today, but it's just products minus reactants. So 100 minus 50 would be your delta H line. All right. Then this right here, I didn't ask you to label, but the distance from reactants up to your transition state. Anybody remember what that's called? What do you, if you get a new phone, you have to take it and get it what? Activate. So this is the
Activation.
energy. Okay. All right, let's add just a little bit more conceptually. So in order to go from reactants to products, you have to break the bonds in the reactants, and then you have to make the bonds in the products. Everybody good with that? Okay, going to break stuff apart and then put stuff back together. So this energy, as you go up, this is you breaking bonds. Okay, so however high that is, that's going to tell you how strong those bonds were in your reactants, because you have to break all of those. Okay, and then when you're going down, right here, you're going to be making. Okay, so going up from 50 to 250, that's how much energy we needed to break them. So we needed 200 to break our bond. And then how much energy did we get back when we made the bonds? 150. So which bonds appear to be stronger? Good, because they were a lot harder to break than we got back when we formed. Okay, and that's what makes this endothermic, because you have to put in more energy than you get out. You have to put in energy to break the bonds, then you get some of it back when you make bonds, but not all of it. So endothermic. Okay, ready to go with that? All right, let's look at the notes we got yesterday. So let me keep my computer up. just go through front, back, okay, one slide at a time. I can't write on the slide, so I'll try to speak aloud what you should write on the slide, and I'll try to say it a couple of times. Okay, this is just an overview of this chapter. So we're going to be looking at enthalpy, which we'll define in a second, calorimetry, Hess's law, enthalpy again, and then the bond energy. Okay, this is a definition of the chapter. Thermodynamics is the relationship between chemical reactions and heat. So we're going to be looking at what causes a chemical reaction to occur. So there you can make a note. We're going to be looking at what makes something spontaneous versus non-spontaneous. What factors decide if something's going to be spontaneous or non-spontaneous. So we learned last chapter that if delta G is negative, it's spontaneous, positive, non-spontaneous. But what decides that? Okay, that's what we're looking at. So spontaneous or not, what decides if it's going to be either or? That's what we'll be looking at. Alright, so we got three main concepts. Enthalpy, so here on enthalpy you want to make a note. Enthalpy is heat. So we're going to represent that with delta H. Okay, and this whole lesson here will be about enthalpy. Then the next section, Thermo 2, is about entropy, which is randomness. Okay, like for example, a gas has more entropy than a solid, so it's more random. We're going to represent that with delta S. Entropy is delta S. And then free energy is delta G, which we've already looked at being positive or negative. All right, this slide is just a definition of system versus surroundings. So the system is the actual chemical reaction. So the system, we can make a note here, the system is the reactants and products. So if you have a balanced equation, your system is just those things that you can see in the balanced equation. And then everything else is your surroundings. No. So, for example, like, you know how we break those things apart because they're dissolving in water, right? So those things would still be part of the system, but the water is going to be your surroundings. So anything that you don't see in the overall balance equation. Good question. Okay. So, for example, like if you're holding a beaker and the reaction's taking place in the beaker, the water, the beaker, and your hand are all surroundings. And then the only thing that's the system is like the atoms that are actually reacting inside it. All right, so for example here, if we're looking at this reaction, H2O solid, which is, what's H2O solid? Ice. So ice goes to H2O liquid. Okay, so ice goes to water. That's the melting process. So the system is the ice and the water, and then the surroundings is everything else. So you have to put heat into ice to make it melt. So you have to take heat from the surroundings and put them into the system. That makes sense? Okay. So this is an example of an endothermic process. Okay. Heat going into the system from the surroundings. If we're endothermic, delta H, I'm going to make a note out here about endothermic. Delta H is going to be positive. Delta H positive. All right, exothermic is a reaction in which heat flows out of the system. So, for example, here you've got the burning of methane. So methane and oxygen, carbon dioxide and water, those are your system, but then your surroundings will be everything else. So when we burn something, we're the surroundings, so we feel the heat. So it's giving off heat to us, the surroundings. So this is an example of an exothermic, and delta H will be negative. Alright, this type of reaction is favored. Okay, we would rather have an exothermic than an endothermic, because an endothermic, we're going to have to give it heat to make it happen. So an exothermic would be a more favored reaction. So these are more likely to be spontaneous. Okay? They're not always spontaneous, they're more likely to be spontaneous. Okay, because they are favored. We don't have to put any heat in. Alright, first equation. So there's a lot of equations in these notes. For delta H is the heat of the products, or the enthalpy of the products, minus the heat or enthalpy in the reactants. Okay, so products minus reactants. So just be careful to not get them flip-flopped. Okay, final products minus initial reactants. So that's exactly what we did on the bell ringer. We did products 100 minus reactants 50. We said delta H was 50. Okay, positive 50. If it would have been exothermic, like down here, we would have said 25 minus 50. Negative 25. So exothermic will give you a negative delta H, but you're still doing products minus reactants. So don't worry if it's negative. Okay, it should probably be negative if it's exothermic. Two example equations with their delta H values already calculated. We have the burning of hydrogen fuel and then the making of hydrogen gas. Okay, what is the relationship between those two equations? Okay.
Both oxygen and hydrogen are about it.
Yeah, but what did they do to get from this reaction to this reaction? They just flipped it over, right? And then what happened to your delta H value? To positive, right? So remember from last chapter, we flipped the equation, we flipped the sign? That was on delta E, right? But same thing here. So if you take your equation and you flip it over, your delta H value is just going to change your sign. Okay? And the reason is because if we think back to our chart here, I keep clicking on everything. If we think back to here, okay, if we go forward, we gain 50, right? But if we went backwards, we would just lose 50. So if we went backwards, it'd be negative 50. If we go forward, it'd be positive 50. Okay? So that's why it's the same sign if you just flip it over. All right, and there's just kind of a picture to illustrate that. Got water down here in energy, hydrogen and oxygen up here in energy. So if you go up, it'll be positive, and if you go down, negative. Same distance, just different direction. All right, so there are 4 ways that we can find delta H. And you'll have to, on the test, figure out, okay, which method should I use? I got 4 ways that I can find delta H. And the first one is using a calorimeter, which is just an instrument to measure heat flow. So it's not real complicated. Calorimeter looks like this. You've got a styrofoam cup with a thermometer in it. Okay, and then you can use something to stir, or you can just stir with your thermometer. And you're just trying to see how much the temperature changes as the reaction goes. So you put a lid on it to trap the heat, and then you can just stick your thermometer through that little, it's really a coffee cup, and you just stick your thermometer through the place that you'd normally drink out of. So if your temperature goes up, you know that your reaction is if the temperature goes up, the water's getting warmer, so the reaction must be giving off heat or taking it in? Giving it off, because water's your surroundings, right? So if the reaction's giving off heat to the water temperature goes up, so the reaction must be exothermic. But then if the water temperature goes down, endothermic, okay? Alright? So that's how you're going to measure. But like in last year we would just say, oh, this is endo, this is exo. But now we want to say this released this many kilojoules, or this took in this many kilojoules. Okay? So this is the equation that we'll use. whenever you see a calorimeter problem, and it'll be really clear, like they put this in a calorimeter, you want to think about this equation here. Okay? Delta Q equals MC delta T. Okay? Q equals M cap. You want to think about that if you see a calorimeter problem. So Q is heat. Now, what did we say heat was before? What letter did we give it in the previous examples? Delta H. Okay? So let's make a note off to the side here. Delta H and Q are related, but not the same thing. So delta H is Q divided by moles. And just one more note, that's moles of your reactant. Okay, so in a calorimeter, we'll use Q to then find H. So Q is heat, and then Q can use to be find H, and H stands for, starts with E. Enthalpy. Okay, so enthalpy equals heat over moles. So they're basically the same thing, but H has moles and then Q doesn't have moles. Right, so Q equals M, which is mass, and that's going to be the mass of the water or solution. Okay, or solution. So almost always you make a solution with water, but if you make it with something else, it'll be the alcohol or whatever you make your solution with. Okay, but it's usually water. So that part is really confusing to people, so you probably want to circle the water part, because you'll be like, mass of what? Because there's usually more than one mass in the problem. So it's the mass of the water, or whatever you're making your solution with. Alright. C is the specific heat capacity of the water. This is a constant. Okay, so for this one, now I'm going to draw an arrow up. For water, your C is 4.184 joules / gram times Kelvin. Okay, that's the one for water. Notice they give you the value for iron and for some other things. So if your solution is not made out of water, then you would find a different C. You can like look that up in a book, or they'll give it to you in the problem. Okay, it's not something you have to calculate. Okay, and then delta T is our change in temperature, final minus initial. Keep that in mind. You always want to do final minus initial, and you might get a negative number. So this is Q. This is the mass of the water, and the C for the heat capacity for the what? Water. Okay, so you may have a little chart, and you have to pick one. So it's the mass of the water and the heat capacity of the water. Now, if you're not using water, it'd be like mass of the alcohol, heat capacity of the alcohol. So whatever your mass is, your C should be of that same thing. Okay? All right, so if this is all about water, let's make a note. This Q is going to be for the water. So you can see right there, Q. That's the heat lost or gained by the water. Okay, so this whole equation basically is about the water. So remember our example before. If the water gains heat, the reaction is?
Indo. It's Indo. No.
Just loses or gains. If the water gains heat, the reaction?
Indo.
Lost or gained? If the water gained heat, the reaction must have lost it.
Oh,
right?
oh.
And if the water loses it, the reaction's gaining it. Right?
Yeah.
If the water loses heat, the reaction's gaining heat. Okay? If the water's gaining heat, the reaction's losing heat. Okay, it says it on this slide, but not in those exact same words. Okay, so I think that's 2 slides forward. The heat lost or gained by the water is equal but opposite to the heat lost or gained by the reaction. So if the water lost, the reaction gained. If the water gained, the reaction lost. Y'all see that slide? So for example, if you use that equation and you find delta Q to be positive 568, Q for the reaction is negative 568. Good. Makes a sense. Okay. If you find the water to be negative, the reaction's Q will be positive. Okay. So you just got to remember to flip your sign, because what you're calculating is Q for the water, so Q for the reaction is the opposite of that. All right. Let's do an example. Okay, what if we take 0.075 moles of hydrochloric acid and 0.075 moles of sodium hydroxide, and we add them both to 150 milliliters of water in a coffee cup calorimeter. Okay, so you see in the question calorimeter, you want to think about your Q equation. The temperature of the solution increases from 23 to 29.9. Calculate the enthalpy. So they want me to calculate delta H, but I have to calculate Q first, right? So that can be Q over moles, find delta H. For the formation of 1 mole of water in this reaction, assume no heat is lost to the surroundings. So in that coffee cup, of course, all of the heat's not going to go to the water. Some of the heat will go to the air and stuff. But you have to, for ease of math, assume that all the water is going to take the heat. Okay? So find Q first, and then we'll go from there. So to find Q, we're going to do delta Q equals. Okay. Alright, so mass first. Delta Q equals the mass of what? Water. What did they tell us about the water?
150 milliliters.
Okay, good. 150 milliliters. Now, an important fact about water is that 1 milliliter equals 1. For water, 1 milliliter is 1 gram. Okay, so that was, I think, confusing for some on the stoichiometry stuff, because they gave us grams of water and we were trying to do molarity. So if they give you grams of water, you can just change it straight to milliliters. Correct. 150 grams of water. Times C.
The Q over water.
Yep, that 4 number from 2 slides ago. 4.184. What's the unit? Joules. Okay, good. Alright, so your C is going to be found here on this slide. 4.184 joules/gram times Kelvin. Alright, so according to that, what does our temperature need to be in? Kelvin. Alright, now we're trying to find the change in temperature, right? So we're going to subtract. So let's do it before we change it to Kelvin and then change it to Kelvin and compare. Okay? So what is the difference right here? 6.9. Okay? So 6.9. I'm just going to write that down here. Alright, now how do you change stuff to Kelvin? Add 273. Alright, so add 273 to both of those and then subtract them from one another. Change both of them to Kelvin, so add 273 to both of them, and then you still want to subtract because you're trying to find the change. Okay, so if you add 273 to the first one, that would be 296, and then 302.9. Okay, and then when you subtract them, what do you get? 6.9. Okay, so what I'm trying to show you is, yes, it's supposed to be in Kelvin, but when you subtract, you get the same answer. So it really doesn't matter as long as it's not in Fahrenheit. Okay, so Celsius or Kelvin, you still subtract, and we can call it Kelvin so our units can cancel. Okay, but when you subtract Celsius or Kelvin, you get the same answer. All right, so what cancels here? And so what's our unit? Okay, so Q for the water. I think it's 4,000 or 43,000. Q for the water. So that means the water gained heat, right? Because temperature went up. So the reaction must have
Lost.
loss. So delta Q for the reaction will be what?
Negative 4,330.
Alright, so there's the math one more time. So you end up with positive 4,330 joules for the water, and then opposite in sign for the reaction. The heat gained by the water is the heat lost by the reaction. So it's X both ends. Alright, lastly we can calculate delta H, which is Q for the reaction over moles. So it's going to be negative 430 joules over, back to the example, how many moles did we have? I don't remember. There we go. How many moles? You just want moles of one reactant. Okay, 0.075. Now, if you have more than one, which we do have more than one here, but if you had different numbers, you would pick your limiting. Okay, like we usually do. So these are the same number then. Where are the chlorine and the sodium in the equation down here? Or why aren't they in the equation?
This is about one.
Because what were you going to say? Spectators. Okay, so hydrochloric acid is a strong acid, so it breaks apart, and then sodium hydroxide breaks apart, and then it'll make sodium chloride, but that breaks apart. Okay, so sodium and chlorine are just left off as spectators. So on the bottom here for moles, we're going to put 0.075. Again, if you had different values, use the limiting value. Okay, and when you divide, you should get negative 580,000.
Yeah. I got negative 500,737.
573.
373.
Okay. All right, and that's joules. And notice they just went back 3 places, so to change it to kilojoules.
I can do this.
That's not right.
I got negative 57733.
Okay, 57733. Okay, there we go. So that makes more sense. Move it back 3 places, so then they just rounded. Negative 58 kilojoules per mole, right? I think they're missing the per mole part. Because you got moles on the bottom. So kilojoules per mole. Okay, good? Okay, so calorimetry, that's the equation that you'll use. Okay, and we'll stop there. The next method is Hess's law. Okay, but we'll do that on Tuesday. So the plan is to do one method a day. Okay, so we'll do Hess's law Tuesday and Wednesday. We might do these two together, pretty easy. Wednesday and Thursday, or just Wednesday. And Monday, I'll give you like a exam study guide. Okay, and you can work on that Monday. Okay, your test grades should be on iNow. If you want to see them, I have them up there. Questions?